Hi, I'm square root of -1, and I have problems with doors. I mean, let's face it, they can be tricky sometimes. First, you've got to figure out if it's a pull door or a push door and get that all sorted out. And then you need to figure out if you need to push or pull on the right side or on the left side of the door. And then you have to figure out how much force you need to actually open the door. And then you have to remember to tense your arm. I'm serious, I've walked up to a door, put my arm out, and then just forgot about it and walked face on into it. Really embarrassing. Anyway, and then assuming you get the door open, you need to time when you actually release the door so you can get through it. And then even if you do get the door open at the right time, you still need to aim your body so you can get through it. So yeah, doors are kind of a personal nemesis. And so I've challenged them to a
physics battle.
That's right, you heard me. This one's to the death, or maybe just a concussion. So here's how it works. For each of the ways in which doors manage to defeat me, I need to defeat them using physics. If I can explain a concept in under a minute, I get a point. Otherwise, doors get a point. This video is obviously edited, but I promise each of the individual explanations is live, real-time, and unscripted. So here goes. Wish me luck. Alright, so I'm ready to go. I have my notebook and pencil, calculator, and I have an online timer set up for 1 minute, so it's screen recording. Hopefully you'll be able to see that as well. Okay, first 1 minute. Let's go. Start. Wait, didn't start. Okay, start. All right, first one, push versus pull door. Actually, I put this first because I don't think I can do it because it's not even physics. It's just me not reading signs or there not being signs. So yeah, put a sign on your door that says push or pull and I'll try to read it. I probably won't succeed, but that's what I should do. So yeah, that one I forfeit to doors. Okay. Second one, right versus left. This I can't explain. Start timer. So, torque works as follows. I am going to write this down in my notebook, which you won't see, but that's okay. So, you have an object that has an axis of rotation on one side, and so the torque on that is what's going to cause it to swing around the axis. And torque equals the distance from the axis of rotation times the force that you use times the sine of the angle between that distance vector and the force vector. So basically the lever arm R is going to be small if you're right at the point of rotation, and it's going to be big the further away you are. So the further away you are from the point where the door hinges, the greater torque you're going to get, the more you're going to be able to actually open that door. Yay, just in time. Okay, next one. So how much force do you need to actually apply to that door to get it open? I think I need to do this one with numbers, which might be hard because that will need some values, which I don't know, so I'm going to have to estimate them, which I'm bad at, but we'll see how that goes. All right, let's go. Okay, so let's say a door weighs 50 pounds. We need to open it with our arm using a torque on that door, which needs to be large enough to counter the torque due to friction. Torque due to friction is coefficient of friction times the normal force, which is just the weight of the door, times the radius between that source of friction and the center of rotation. So basically the radius of the hinge. Let's say it's a 1/4 inch, so about 0.02 feet. So then let's say mu for steel hinges, let's say it's 0.5. So 0.5 times 50 times 0.02, that's 0.5 foot-pounds. And then to get the force that we need to apply, we need to divide that by the distance away that you're pushing. So let's say you push 2 feet away from the hinge. So divide by 2, that's 0.25 pounds of force. Whew. Right? That's just to get it going. And we're also ignoring friction due to the actual door frame, but like that's an idea. Also, 50 pounds might be a bit much for a door, so maybe I got that wrong. We'll check later. I'll figure out how heavy a door is. Get a door here to weigh somewhere. Okay. I don't know. I wanted to see what the actual weight was, so I got a door out, but the scale's not working, so I don't know how I'm gonna measure that.
Okay, so it was really bothering me that I couldn't figure out how to measure the weight of that door without a scale because it's broken. So I made a compromise and I made myself a new scale. So basically, I have this piece of balanced wood tied to the tree, and I have the door, and I have a grocery bag which is going to be filled very soon with these dumbbells. And so we're gonna compare the weight. Already by bringing out here, I'm pretty sure this door is not 50 pounds. Maybe 50 pounds is like an outdoor door. I don't know. Anyway, we're gonna find out. So bear with. Oh my gosh, my door is suspended and it's like hanging pretty even with a 15-pound weight. Is it a 15-pound door? Now I feel really weak. I guess doors are kind of harder to carry out.
Okay, so that was pretty exhausting. I finally got the door back in, towed in all those weights. I brought out way more than I needed, but that's okay. Now we know I'm bad at estimating things, which we already knew, but that's okay. And now we know how to measure the weight of something, so I still have that little contraption whenever I next need it. But everything's back in, so no more excuses. We're done procrastinating. Time for the next challenge, which is actually tensing your arm so that you don't just walk into the door. We're gonna make some assumptions and say that you're just gonna have your arm out and just keep it tense rather than moving your arm, because that would change angles and make things complicated. So we're just gonna walk at the door with your arm like that. And start. Okay, so let's say that this is flat and this is a 90-degree angle. That simplifies things because then if we have a force going straight in, there's no torque around the elbow. Realistically, there'd just be some muscles just to stabilize that. But we're just going to talk about the pectorals and the torque around this whole piece of arm. So we got the force here at like a foot from the center of rotation, and the force from the pectorals, let's say it's at 30 degrees, 1 inch down your arm. 2 inches down your arm. Okay, so that means that 2 inches times the tension times the sine of 30 degrees equals 1 foot times the force. So then tension equals 1 foot divided by like 0.02 feet divided by sine of 30 is 100 times the actual force that you need to apply. Boom. Just in time. Okay, next one. So when should you release that door? Assumptions, let's say you get the door open at a maximum right when you are entering the doorway, and let's say that that maximum is 90 degrees. Okay. Starting timer. Now. Okay, so for doors that are going to swing back closed after you, when are you going to let go? Let's assume that it's going to take the door 5 seconds to swing back. So, and 2 foot wide doorway. So what we need is, assuming you take up the middle foot of that, we need to find when that angle of the door is too much for you to be able to keep walking straight. So if we draw a triangle, there's the half of the foot to the right of you, and then the hypotenuse is the 2 foot wide door. So then that means that the angle is inverse cosine of 1/2 over 2. So that's 75 degrees. 90 minus 75 is 15. The door can have moved by 15 degrees. If it takes 5, oh my gosh, this is not happening. I'm going to keep talking. If the door is swinging shut from 90 degrees and takes 5 seconds, then you are doing 18 degrees per second, which means that that 15 degrees should take 0.83 seconds, and then it takes you some time to get to that point where you're getting past that part of the angle. So let's just say that's approximately 2 feet, because it's close enough. It's just close enough to being straight out. So let's say you walk up 2 feet per second, so it takes you about a second to get there. So 1 second minus the 0.83 seconds is 0.17 seconds, which is how long you should wait before you let go of the door. If I win this last one, I win, and if I don't, it's a draw. So the last one is going to be aiming yourself to actually get through that open doorway. So we're just going to assume it's an open doorway without there even being a door in it, and just like corrections for entering along the wrong angle. Let's go. Okay, so when you're coming at a door, first let's say you're going straight at it. Then you're going to have a certain angle in your vision between a straight line in front of you and the two sides of the door. And ideally, they're going to be the same angle both directions. So what would that angle be? So if let's say you're 2 feet away, so then you have the door, and let's say it's 2 foot door, and then you're 2 feet away. So then you have a triangle. We can take inverse tan. I guess that part would be 1 foot because it's half of that. So then it'd be like a 25 degree angle, because inverse tan of 1/2. So then in general, that angle would be the inverse tan of like half of the door over the distance you are away from the door. But in general, this makes sense because you're always trying to get to a point halfway between the two sides of the door. So you're always trying to bisect that angle. So you always want the angle on other side from straight to the two sides of the door to be equal. That's how you're going to get into the door. Yay. Okay, so we're all done. I'm going to tally up the points. And if you disagree about how I did this, or my explanations, then please let me know in the comments section, and maybe we'll have a rematch or fix some of the points. But thanks for watching. This was fun and scary at the same time. Wow, so I actually won. Maybe I'll be better at getting through doors now. Ugh, or maybe not.